So today we are going to start on our last two, or do our last two trends, the first one of which is electronegativity. Super important you know with what electronegativity is, what it's about, and it has to do with the attractiveness of electrons to an atom in a bond. So a lot of times we talked about polar and nonpolar bonds. How we figured out whether bonds were polar or nonpolar was looking at differences in this so-called electronegativity. You can see in this little description here, you need to think about it like a tug of war. The higher the electronegativity of an atom, the closer it's going to hold. It's comparative. It's going to hold, in a bond, you've got two atoms. The one with the more electronegativity is going to hold the electrons closer to it. So the trend, as you go down the table, electronegativity decreases. Why is that? Well, think about those valence electrons at the bottom of the periodic table if you're going down the table. These valence electrons are a lot further away from the nucleus up here, so there's going to be less of an attractiveness to that nucleus due to increased shielding. Going down the table, the reason is always increased shielding. You can also look at Coulomb's law. The distance increases as you go down the table, so that attractiveness decreases. Okay? Across the table, we have an increase in electronegativity. This brings to mind fluorine the floozy. Fluorine is the most electronegative element on the periodic table, and if you're in class, you can see her picture hung up, her little character hung up underneath the board. The closer something is to fluorine, the more electronegative. Why? Fluorine is super small. It's got a very high effective nuclear charge. So why isn't the noble gas next to it more electronegative? Why not? That's just because of the definition of electronegativity. Those noble gases, that tiny noble gas next to fluorine, also known as neon, doesn't bond. So it can't make a bond. Because it can't make a bond, it can't be attracted, have attraction to electrons in bonds. So there is no electronegativity value for those noble gases. So electronegativity kind of stops at the halogens, at least the values. Again, these are all man-made values and definitions. So if it's closer to fluorine the floozy, it's going to be more electronegative. So number 17 down here, which element is more electronegative, which is closer to fluorine the floozy, potassium or arsenic? Well, arsenic's way closer. Nitrogen or antimony, what's closer? Oh yeah, nitrogen is right next to fluorine. And Sr or Be, strontium or beryllium, what do we think? It is beryllium. Okay, level takes precedence. Whatever's closer to fluorine, or just follow the trend. Strontium was way below beryllium, so strontium had more shielding, so it had less electronegativity. All right, ionization energy. We talked about ionization energy a little bit when you did those PES Pogles, where we talked about the amount of energy it required to remove an electron, and those removed electrons were graphed in the PES. Well, this is actually now looking at the energy holistically. So if I have an element and I apply energy to it, I try to, with that energy, I'm removing an electron. That energy is the ionization energy. The energy required to remove an electron, leaving behind that guy. So, trend again, as you move down the table, due to increased shielding, the ionization energy gets less and less, meaning it's really easy to take an electron away from francium down there at the bottom left hand of the table because he's got so many shielded, his valence electrons are so shielded, there is such an increase in distance, so Coulomb's law, there's very little attractiveness. So as you go down the table, this attractiveness decreases, so it's easier to remove an electron, so it requires less energy. Ionization energy decreases as you go down the table. As you move across the table, we know that that nuclear pull increases, right? So if that effective nuclear charge increases, it's going to get harder and harder and harder to remove electrons as you go across the table Therefore, we're in ionization energy. Ionization energy is going to increase as you move across the table. Now, by definition, we are talking about removing the most loosely held electron. So I can remove one electron, and then I can remove another, and then I can remove another. But I'm removing the most loosely held electron first, and then I remove them one at a time. You can look at a series of electronegativities like this, and I keep saying electronegativities, ionization energies like this, and you can figure out how many valence electrons you have. If you notice, for beryllium, if I remove the first electron, it takes about 900 kilojoules. Yeah, that's whatever. And then if I remove the second electron, the next one, it takes 1760. Sure, that makes sense. It's going to get harder because I took an electron away, right? So I'm becoming positive. I become a positive ion. It's hard to remove negative things from positive ions. So the more I remove, the harder it's going to get. But there's an anomaly that happens specifically for beryllium right here. If I try to remove the third electron, holy cow, it went from 1,700 kilojoules to 15,000 kilojoules. That is a huge difference. When you see a huge difference like that, that means there's been a change in the energy level. That means you are now removing a core electron. So what that means is beryllium really has 2 valence electrons, which it does, right? And that's why beryllium has 2 valence electrons. That's why beryllium makes a +2 charge. Beryllium's not going to make a +3, not with that energy requirement. It'll make a +2. So the reason things have the charges they have is due to this ionization energy. One thing you do need to know, because of course an AP can't go through AP without exceptions, is to talk about the exceptions to the trend. So if you look, I'll show you where they are on this graph. If you go from hydrogen to helium, I'm just going to kind of go from there to there. We're going across, right? So that's an increase in ionization energy. That makes sense. And then as we go from helium to lithium, that's dropping because that goes down the table. And that's lower than that of hydrogen. But if you look, do you see how we have these little dips here? The trend doesn't just go increase straight across. We have the dips here again. All right, so these are exceptions that happen between the nitrogen and oxygen family and between the beryllium and boron family. You do need to know those exceptions and why. So normally, as you go across the table, ionization energy increases. Not in these two spots, though. We get little dips, and we're going to talk about those dips. The first exception that happens, let's look at between beryllium and boron. What I like to do when I explain this, I think it makes most sense if you actually look at the orbital spin diagram. So this is the PES for beryllium. If I have beryllium, I'm looking at this, right? This is a 1s2 and that's a 2s2, right? 1s2 and this is a 2s. If I'm looking at boron, I'm comparing a 1s2, 2s2, 2p1, right? So we are actually comparing the last electron in these. That's what we're looking at. So if the trend were to go as expected, it would be harder to remove the last electron in the P here than it would be to remove that guy. It's actually easier to remove him. So why is that? Well, it has to do with the shape and proximity of the p orbital to the nucleus. This last electron in beryllium here, if you look, is in an s orbital. It's somewhere that distance within this circle, right? But if you know about p's, you see how p's kind of extend further out than s's? They're a smidge further away from the nucleus. So their average distance from the nucleus when they're in the p's is slightly larger. So because it's sometimes further away from the nucleus than the electrons in the s, it's going to make it easier to remove that particular p electron. All right, now let's look at the second exception. The second exception is in the dip occurs between the nitrogen and the oxygen. As we go across the table, it's supposed to be harder to remove the last electron in oxygen if the trend were normal, but it's not. So why easier? Why is it easier to remove the last electron of oxygen as opposed to the last electron of nitrogen? So again, I'm going to draw my little, I've got my S's. So I've got my two S's, and my three P's. And here I've got my S's, and my P's. And in this one I've got four P's. So here, and I've got 1, 2, 3, and I'm doubling up. So why is it easier to remove that electron than to remove that electron? Well, this has to do with the fact that electrons are negative and they don't like each other. So if you look in that particular orbital, there are repelling forces. Because there are repelling forces, it's going to be easier to remove that electron than it is to remove this happy orbital hanging out in a half-filled orbital. So this repelling force that exists between these two electrons makes it easier to remove the last electron in oxygen. Okay, so let's just start answering some questions now, since we've pretty much been over everything. Now it's just a matter of you practicing and practicing. Which atom has the highest ionization energy and why? Chlorine does in this case, and you have to give reasons now. And the reason is that chlorine has a higher effective nuclear charge. Higher effective nuclear charge. Okay, which has the lowest ionization energy and why? Okay, as you go down the table, cesium is going to have a lower. Why? Because the electron, experiences, oops, my thing's not writing anymore. Experiences more shielding. So remember, shielding up and down, effective nuclear charge going across. Which has the larger second ionization energy, lithium or beryllium? Well, lithium does, right? Because lithium's a group 1, so removal of the second electron is removing a core electron. And that second electron is not going to want to go anywhere. Beryllium's second electron is still a valence electron, so that one will be a lot easier to remove. All right, arrange the elements, oxygen, fluorine, and sulfur, according to increasing ionization energy. So we're comparing oxygen, fluorine, and sulfur. Remember, level takes precedence. So the sulfur, being down below, is going to be the one with the least ionization energy. And then fluorine the floozy is super, super highly electronegative, and its super effective nuclear charge really holds onto electrons, so that's going to be the highest of the three in ionization energy. All right, atomic size. If we're going from, I guess we're going to go from small to large. Let's just say it. Oh, it says increasing. Yeah, increasing. I don't need to write small to large there. So the biggest one, because level takes precedence, is going to be your sulfur. That's the one we're going to put as the largest. And then as you go across the table, more effective nuclear charge, that makes F the smallest and O in the middle. All right, electronegativity. This is easy. Fluorine the floozy, it's got the greatest, so that makes it O here and S there. Okay, given the following data about atoms' ionization energies, predict the number of valence electrons. All right, so we've got 700, 1800, holy macannoli, 16,000. So it looks like this third electron is a core electron, so that means that has to be 2 valence, right? So yeah, that's got to be 2 valence, so it could be anything in group 2. All right, trendy thoughts. This is just a little list of some things to think about. whenever you're working trends, follow these steps. First, you want to locate the elements you're comparing and check if it's a matter of being in the same column or in the same row. Okay, if they're in the same energy shell or energy level, we talk about effective nuclear charge. If they're in different energy levels, we're basing it on shielding or Coulomb's law. Okay, you can go ahead and read the rest of this on your own, I think. I think it's a pretty good little review. I do think this last one is super important because it talks about looking at things and seeing if they're isoelectronic to each other. Whenever you have ions, you have to check on that. That's going to be one of the first things you have to do. All right, a couple more questions we'll do, and we'll talk about how you need to answer them. So, 25. Briefly explain the following statements. The atomic radius of magnesium is smaller than that of barium. Whenever you're given something like this, do not contradict the test and say, well, actually, magnesium is larger. No, they're not going to do that. You need to answer the question. They're telling you the fact. You need to now give a reason. Well, we're dealing with something in, what are we dealing with? We're dealing with magnesium, and we are dealing with barium, and those two guys are in the same group. So, magnesium then is smaller because there are less energy levels and therefore, if you want to write therefore, you can write with the 3 dots, less shielding. Is it I before E except after C? It's probably IE, isn't it? Demo can't spell. All right. Part B. The ionization energy of S is lower than P. So if you're paying attention, you can see that S and P is an exception. It's between that nitrogen and oxygen family. So phosphorus should really have a lower ionization energy than sulfur, but it actually has a higher ionization energy than sulfur. And what does that have to do? That had to do with those repelling forces. So how would you explain it? If you want to draw out your orbital diagrams and point to the electrons, you can do that. So sulfur, we know, looks like, its last ones look like boom, boom, boom. Well, I'll do phosphorus here, and then this is sulfur. This one is doubled up. Okay, so what you can then do is explain the last electron in sulfur is doubled up in a p orbital. I'm going to move this around a little bit. So due to repelling forces, it's easier to remove that electron than the last electron in phosphorus. Okay, so you want to kind of indicate, I like to do arrows so the grader knows, you know exactly what electrons you're talking about. It might actually be helpful if I pointed to the right electron. We're pointing to that electron compared to that electron. And so showing the diagram like that, even if it's not labeled that this is a P, your words describe that you get that. It just gives us a clearer picture of what's in your head. Okay, the energy required to remove the 4th electron in aluminum is significantly larger than the 3rd. Well, why is that? The 4th electron is a core electron. and is harder to remove since it's an entire energy level closer. All right. This right here, good news, we're not doing electron affinity anymore. Yay! That was rather confusing and it doesn't show up anymore, so we're taking it out of the curriculum. All right, so you've got some other problems here. You've got three, let's see, 1, 2, 3 problems. These problems, we might get to them in class, we might not, but I'm not going to do them on the video because I am providing you with the answer keys and all the points associated with those. You can find those in the in-class problems, the filled-in ones online. And I also believe with your homework answers, you can find these answers as well. What problems I'm talking about the next ones. So let's look at those. So this problem right here, you'll have the answers for. There's 3 of them. And then you're going to have the answers to this problem. And then you have the answers to this problem. These are all classic, traditional atomic theory periodic trend problems. So I highly suggest you do them and use them for review for the exam. And that is it. You are done with trends.